What's left? We're throwing it straight up. Same building, same ball, throw it straight up. VI equals 3 meters per second. I want to know the final velocity right before it hits the deck. So VI is 3, it's obviously going to go up and then come down. Go up here, come back down. Acceleration throughout the whole trip is still minus 9.8 meters per second squared. And my displacement, I'm still on top of a 2-meter building. All right, I got 3 things. Let's solve. VF squared equals VI squared plus 2AD. VF squared equals VI squared, looks like 9, plus 2 minus 9.8 times minus 2. You're going to wind up with the square root of a positive number. Which one are we going to choose? We're going to choose the negative. So the velocity right before it hits the deck, minus 6.9 meters per second. Same as the first one we did yesterday. We did previously. Okay, minus 6.9. Question is now, what is the hang time? It's coming up and it's going down. VF equals VI plus AT. VF is minus 6.9 equals, the VI was 3 plus minus 9.8 T. Crunch that. The hang time comes in about 1.01 seconds. Because it's going up, coming down here. Now, some of you are going to have a hard time because this is a little non-intuitive, isn't it? Because all we're looking for is the displacement from here to here. It doesn't look like we're accounting for the fact that it goes up, reaches a peak, and comes all the way down. When we get into class, we'll explain that in further detail. Trust the algebra, though. The algebra, these linear equations, knows that it's going up, knows that it's accelerating down, and knows that the displacement is minus 2 meters, okay? I don't care what it does up here. The algebra will tell me the hang time by using a displacement of minus 2 meters. It works. It's worked for hundreds of years. It's going to work for Hawthorne next year, okay? So the hang time is that, the final velocity, minus 6.9. All right? Now, a tricky part of this idea of throwing a ball straight up. We still have a building that's 2 meters tall. We're still throwing up at 3 meters per second. Acceleration is down because it's being forced down at minus 9.8 meters per second squared. Now, a good question would be, how high does it rise? And we're going to call that displacement peak. Displacement to the peak. How high does it go up here? And what is the time it takes to get to the peak? Okay? So let's look at that ball. You throw a ball straight up. You throw a ball straight up for a millisecond. What does it do at the top? I hope I'm not cutting you out there. For a millisecond, what does it do at the top? For a millisecond, it stops at the peak. I'm going to say VF equals 0. Right here, final velocity, because I want to know the peak. The final velocity at the peak is 0. I got 3 things. Initial velocity, 3 meters per second at the top of the roof. Acceleration as soon as it leaves my hand is minus 9.8, and the final velocity is 3. Let's find the hang time. 0 equals 3 plus minus 9.8 t. T looks like it's going to be 0.31 seconds. So it takes 0.31 seconds from the millisecond it leaves my hand to reach the peak. And what is d peak going to be? Three times 0.31. plus 1/2 minus 9.8 0.31 squared. So how high does it rise? It rises about 0.46 meters, 46 centimeters, half of a meter. Okay, so free fall problems, this is always on the test. How high does it rise and how long does it take to get up there? In addition to what's the final velocity down here and what's the time to get down here. So for a free fall, we see three types of questions. Question number one, we reach over and drop it. VI equals 0. That was this one here. Question number two, we reach over and throw it down. VI equals -3. Notice the acceleration and displacement is the same for both of these situations. And now the question is, how high does it rise and what's the time to the peak? And here you have to remember that VF at the peak is equal to 0. For a millisecond, it stops up there. Okay? And I know we talked about it in the earlier videos, acceleration and velocity. How do you speed something up? When the velocity and the acceleration have the same sign, it speeds up. When they have opposite signs, it slows down. So, if I have a ball and it has a velocity of 3 meters per second, it's going that way. If the acceleration is 2 meters per second squared, it's speeding up going that way. If the acceleration is -2 meters per second squared, it starts off at 3, slows down, stops, and then comes back this way. And it's the same thing with free fall. If my initial velocity is 4 meters per second, it's going up. The acceleration is -9.8. So as soon as it leaves my hand at 4 meters per second, what's it doing? It's slowing down. Eventually it's going to stop, and down, coming over this way, the velocity is negative and the acceleration is negative. Therefore it speeds up, and we see this all the time. When you throw something up, reaches a peak, comes back down, it speeds up. So the two signs are the same, it speeds up. The two signs are opposite, initial velocity positive, acceleration negative. It slows down, comes to a stop, and then speeds up because both the velocity and the acceleration are negative. Okay? I have an empty class today, so I'm talking to myself. Please, this is the end of the linear motion problems. Make sure you do the problems at the end of each of the 3 videos. If you have questions, please send me an email. I will be putting notes on Twitter. If there are questions, I'll answer those questions on Twitter, and I would send you an email specifically. If you don't have Twitter, just keep an eye on my webpage. If there's common problems with these 3 videos, I'll post it on my webpage. Or send me an email, whichever is easier. Okay, I hope you're enjoying your summer, and we'll see you in September.